Right, a beta emitter has 6 by 10 to the 20 undecayed atoms present in a sample at a given instant. If its half-life is, if its half-life is 4 minutes, find its activity. I know I'm distracted. I'm trying to get the page of the formula and tables book that we need, which is here. And I'll put it into the homework journal. Where are we? Here. Oh my God. Okay. Sorry, so I have it here. Right. So a beta emitter. So my formula for half-life, as in, they're asking us for the activity. So that's what I'm going to need to use. Activity is lambda n. The number of undecayed atoms I have, so activity is lambda times 6 by 10 to the 20. And then they give me the half-life. And if I go over here, so the half-life is ln2 over lambda. So the half-life is ln2 over lambda. The half-life is, 4 minutes? So 4 minutes, if I multiply that by 60, I get 240 seconds. So that's the half-life. What was that? 240. Okay. So 240 equals ln2 over lambda. If I multiply across by lambda, and then divide across by 240. So I get lambda equals ln2 divided by 240. So it's 2.88 more decimal places by 10 to the minus 3. So I'm going to put that in over here then. 2.88 with more decimal places by 10 to the minus 3 multiplied by 6 by 10 to the 20. So multiplied by 6 by 10 to the 20, and I'm getting, find its activity. So its activity is 1.73 by 10 to the 18, and that should be becquerel. Okay, that's that one. 16. So if a sample of radium contains 2.6 by 10 to the 21 radium-226 nuclei, and it's emitting 3.5 by 10 to the 10 particles per second, calculate the decay constant. So particles per second is the rate of decay, and the rate of decay is activity. So activity is lambda over n, lambda times n. This number here, so particles per second is the rate of decay, and the rate of decay is the same thing as the activity. So that's going to be 3.5 by 10 to the 10. Lambda we don't know, and n is the number of nuclei, which is 2.6 by 10 to the 21. Okay, so we divide by 2.6 by 10 to the 21 and divide by 2.6 by 10 to the 21. So lambda is 3.5 by 10 to the 10 divided by 2.6 by 10 to the 3.5 by 10 to the 10 divided by 2.6 by 10 to the 21 is 1.35 by 10 to the minus 11 per second. Yeah. And then the last one there, which is from a different section. So number 3. A sample of polonium-218, which is an alpha emitter, has a mass of 2.4 micrograms. Calculate the number of alpha particles emitted per second from the sample if its half-life is 3.1 minutes. Right, so polonium. I'm going to go in here. Is it here? Must be further down here. Yeah. So polonium, what's the atomic number of polonium? I have absolutely no idea. Maybe I should check that first. Save the wild goose chase. So polonium. There it is there. So polonium is 84, and in its natural state it's 84,209. We're talking here about an isotope, which is 84,218. Homework. Okay, so polonium is 84,218. So the second questions that I kind of did on the video, the mass number of grams contains Avogadro's number of atoms. Now, Avogadro's number, like I said, it isn't technically on the course, so there it is there. But it isn't technically on the course, so you will have to be given it. Sorry, I'm just putting it into my calculator so I have it. Homework. So the mass number contains 6.0221415 by 10 to the 23 atoms. The sample here isn't 218 grams, it's 2.4 micrograms. So it's 2.4 by 10 to the minus 6 grams. And we want to know basically how many atoms does that contain. So the easiest thing is to go back to 1. So we do that by dividing by 218 and then up to this number. So we multiply by 2.4 by 10 to the minus 6. Apply that maths on this side. So we're going to divide by 218 and we're going to multiply by 2.4 by 10 to the minus 6. 2.4 by 10 to the minus 6. Okay, so I have 6.0221415 by 10 to the 23 divided by 218. Multiplied by 2.4 by 10 to the minus 6. So I am getting, I'm just going to get rid of that box, that this mass that we're talking about contains 6.63 by 10 to the 15 atoms. Okay. Calculate the number of alpha particles emitted per second. So the number of alpha particles emitted per second is again the rate of decay or the activity. So we're looking for the activity, and the activity is still lambda n. So we know how many atoms we have, so we know n, but we don't know lambda but they've given us the half-life. So T a half is ln2 over lambda. The half-life is 3.1 minutes. So if I multiply that by 60, I get 186 seconds. So that goes in here, so it's 186 equals ln2 over lambda. Same again, we did a minute ago, multiply by lambda and divide by 186. So I get lambda equals ln 2 divided by 186. 3.73 by 10 to the minus 3. And then I have n here, obviously lambda here, so I put them together. So I get 3.73 by 10 to the minus 3 multiplied by 6.63 by 10 to the 15. And the activity is that by 6.63 by 10 to the 15. I'm getting 2.47 by 10 to the 13. Oh, sorry, BQ, Becquerels. I will check that they're right. I don't have the book here, but I'll check. But yeah, hopefully that's okay.